So thanks a lot, Rainer, for the nice presentation, and thanks a lot to the organizer to give me this opportunity to speak about a very particular application of clays, which is in radionuclide waste repository. So the aim of this presentation is to explain the basis of radionuclide migration in clay and the key aspects for radioactive waste repository. So I will start with a brief introduction about the generality of radioactive waste disposal and specifically in the concept of deep geological repository. I will speak about which is the concept of safety case, which is the case in which all the researchers are working. And in this context, I will speak about the importance of clays in this radioactive waste repository. Then I will try to give the basis of the radionuclide transport and retention processes, identifying the key parameters that are driving these processes, and then try to outline the importance of studying geochemistry and also geochemical modeling in order to give a mechanistic understanding of the processes that are underlying the transport and retention processes. And then I will make a small overview about the potential factor which can enhance radionuclide mobility, like ligands or colloids, and for this reason, because they can affect safety, are important to be studied. And then I will draw some conclusions. So everybody knows that radioactive waste is generated continuously from industrial, medical, or research activity. And then in radioactive waste, we have radionuclides, which are elements in unstables, which, that undergo to alpha, beta, or gamma decays. And one of the parameters that is important for these elements is they have time, which is basically the time needed to decrease their activity to 1/2. So simplistically, we can divide our waste depending on the half-time. So we talk about low intermediate legal waste when we have radionuclide with half-time lower than 30 years. And in that case, we can store these elements in surface installation. For example, this is the installation of the Cabril, it's in Córdoba, in Spain, in which the main containing and confined material actually is cement. But actually, the main social concern is related to high-level radioactive waste, and especially by the spent fuel, which is generated by nuclear power plants. In that case, we can have radionuclides with a very, very high long time. This is an example of 235 uranium, which has a half-life of more than 700 million years. So these are actually the residues that are of concern. In high-level radioactive waste, a part of uranium, due to the fission process, we have many different radionuclides, the fission products, obviously, but also activation products and also different actinides in small quantity. And all of them have different properties, so we have to analyze these physicochemical properties for all these radionuclides because they deal to different radionuclide migration process. It is also of interest to see that there are several long-lived fission products which have a very high long half-life and are of concern in this scenario. So the most internationally accepted option for high-level radioactive waste disposal is the deep geological repository, DGR. So these DGR are the most sustainable and safest option so far for the final disposal of radioactive waste. This is a very heard statement, but it is based actually on more than 30 years of interdisciplinary research all over the world that has been supported by various international and national programs. For example, in Europe, Euratom has supported many projects, but also there are other organizations which do that. For example, the International Atomic Energy Agency or the Nuclear Energy Agency. So most of the aspects, from the social aspect or the environmental aspect, security aspect, are analyzed in this kind of programs. So what is a biological repository? Basically, we want, which is the main aim, is to try to avoid or delay radionuclide migration until the radiological hazard is not is insignificant both to human and the environment. It is a passive multi-barrier system. It is passive, it means that when closed, it does not need control anymore. And multi-barrier, obviously, because we need many barriers from the waste to the biosphere, or the geosphere, and many barriers are interposed. The engineered barriers compose the near field, which is basically the waste, the canister, which is metal canister, normally, and in the, for example, in the Spanish concept, we have bentonite clay compacted at high densities. Then it's deep because these galleries are put in suitable geological formation at 100 meters in depth. So geological formation, we are selected because they have been stable over a time scale of million years, so in a time comparable to the half-life of our radionuclides. And the most important geological barrier are crystalline rocks, salts, but clays also. So I want to simply to say that these kind of materials have been studied during a lot of years. And the study have been made at different scale, from laboratory to real scale, and also we have made also many studies in underground laboratory. For example, here there are two examples of two underground laboratories. The first one in Switzerland, the Grimsel test sites, which is in crystalline rocks, and in Sweden we have Hässleholm, which is also in crystalline rock, where the behavior of bentonites have been studied in experiment that lasted more than 10 years. And also, there are sites in which the clays are studied as possible candidate to host a DGR. We have in Switzerland, for example, the formation of opalinous clay, and the site is in Monterrey. In France, we study the Calov-Oxfordian clays, and the site is Bure. And in Belgium, we have the studies about the boom clay in the sites of Harz. So, what is the significance of the safety case? We basically have to answer to several questions. This is the safety case, to answer to questions that are dealing with a possible problem related to the safety of this kind of system. So, what are the processes that are actually relevant for safety, which must be included in PEA calculation? Because we need to ensure this safety, we have to make performance assessment calculation, which is basically the calculation of the possible risk, which is translated to the maximum doses that we have at different times. So, which processes can be and must be included in PEA calculation? What parameters are needed for the calculation and how we can obtain them? And after that, are we able to model all these processes at different scales in time and space? And are we able to make simplification without a loss of significant details? This is basically the concept of simplification. So we need detailed and quantitative understanding of all the processes that affect the repository, together with the possible uncertainty associated. and to know also how each barriers may contribute to the confinement and retardation of the radionuclides. So for all these things, we need research. So, for example, which are the key requirements for a clay barrier? We need the clay barrier to have the ability to close any gap to avoid the entrance of water to the waste. So for this reason, in general, swelling clays are used as engineered barriers. But then we need also to be sure that the material is durable, so it has to have a resistance to thermal, hydraulical, mechanical, and also chemical stresses at the long term. So all the studies that we have to perform must ensure that permanent damage to the barriers does not occur. But also we have to understand which can be the effect of coupled processes and, for example, the interaction with other barriers, for example, the canister corrosion processes, cements from the backfills, and so on. And if all these processes can or not affect not only the barrier, but also the migration of radionuclide within the barrier. And finally, this is the point which is probably the most important for radionuclide migration, is that they have to have low hydraulic permeability in the saturated state. Because if the permeability is low enough, this ensures that diffusion will be the dominant transport mechanism. There will be no flow, no advection, so we can somehow to control better migration within the clay. So diffusion limits the transport of aqueous ions to the waste, so this is important because it will delay the canister corrosion and rupture, and then when the canister has broken down, then it will delay the radionuclide release to the geosphere. So diffusion is a very well-known process in which we have a gradient of it is driven by a gradient of concentration. So the first Fick law says that the mass flux per unit area will be proportional to the concentration gradient. And the constant of proportionality is the diffusion coefficient, which is the most important parameter for migration in clays. So when we introduce also the variable time, we will have the partial derivative equation, in which the main parameter still is diffusion. But obviously, when we have a porous media as a clay, we have difference with respect to the liquid because we have to consider that actually diffusion is not in free water, but it is in the pores, the water contained in the pores. So we have to define a diffusion coefficient in the pores, which must be expressed considering parameters like porosity or water content, epsilon here, but also on geometrical properties of the porous structure. For example, constructivity, here is an example, and tortuosity. So here we have two important parameters, which is the effective diffusion coefficient and porosity, and then we can rewrite with respect to the diffusion coefficient in the pore, again the second Fick's law. But the most important process, which is also delaying radionuclide migration, is sorption, which is a process in which simplistically aqueous ions are retained on the surface of a solid by chemical or electrostatic interaction. This is a safety function of the barriers. It's a very important process because sorbate species will suffer a further delay in migration. So we can define also another important term, which is the retardation factor, which represents the ratio between the velocity of water and the velocity of the element which suffer retardation. Sorption actually is expressed quantified by the distribution coefficient, Kd, which is the ratio between the absorbed here and solute species after the equilibrium. This is determined by batch sorption experiments that are sketched here. So it consists in mixing our adsorbent, adsorbate, and then after a contact time to separate and to determine the absorbed versus the quantity of radionuclide that has remained in the liquid. This is a sketch, an example of the effect that can have the Kd, so to have absorption in a system with the same effective diffusion coefficient. At the same time, we observe that the distance traveled from the source when the Kd is the higher, the distance is the lower. So this is important retardation process. So when we deal with a porous medium, we can define the retardation factor in respect to the Kd value, and we can define here a capacity factor, which is the sum of the porosity plus the dry density and the Kd. So we have another important parameter, which is the apparent diffusion coefficient and alpha, the capacity factor, and then we can rewrite again the second Fick's law in terms of this new parameter, including sorption. So all these parameters, the transport parameter, must be determined experimentally. So we have here an example of the most important experiment that we can do to determine the diffusion coefficient. And we have basically two different types of experiment: the true diffusion experiment and the in-diffusion experiment. We will select one type or another depending on the radionuclide and clay system, and then we can rely to analytical or numerical simulation to interpret the diffusion results. So in the case of true diffusion experiment, we have to force the diffusion through our clay. So we study basically the evolution of the radionuclide concentration in an inlet and in an outlet reservoir. And we can maintain here a constant gradient or to maintain a different variable gradient, depending also on the system or the type of experiment that we have to do. But also we have the opportunity to measure directly the radionuclide profile within the clay, and these are called in-diffusion experiments. So through diffusion experiment, we can determine basically effective diffusion coefficient, but also the porosity of the system. And in the case of in-diffusion experiment, we will determine the apparent diffusion coefficient and the alpha factor. So this is an example of diffusion of non-sorbing species. They are conservative. This study is very important because, for example, if we use tritium or treated water, this will provide generally the upper limit for the diffusion coefficient. So this is the maximum diffusion that we can have here. So these are a study made with tritium, with neutral species, and with chlorine, which is also not sorbing, but it is negatively charged. So we can see here the experiment have been made as a function of the dry density. So we have a slight dependence with the dry density for tritium, but much more dependency on the dry density for chlorine. This is why, because we have also measured the accessible porosity in this test, and we observed that the total porosity, that the theoretical one, is quite similar to that determined for tritium, but in the case of chlorine, we have much less accessible porosity. So that means that porosity that we can calculate by means of the water content is not always completely accessible to species like the anions. So this is a phenomenon. This is called anion exclusion, which depends on the charge of the radionuclide and the clay, but also on the compound density and also on the water chemistry. This is due to the fact that the clay is negatively charged, so it produces a double layer here in which anions cannot enter to the are for the electrostatic repulsion, they can have not access to all the pore. This is interesting to see that if we have a diffusion coefficient of 10 to the minus 12 in the square meter per second, simply calculated with the simplest diffusion equation, to travel 1 meter, we need 3,000 years. 30,000 years, sorry. So, for the safety, this is okay, but we have to consider that these short diffusion lengths generally represent an experimental challenge to measure these kind of things. The experiments are actually time-consuming and complicated, above all when we want to go to large, more realistic scale. In this case, this is an example of a diffusion experiment made in opalinous clay, in which also we observe a sort of an isotropy in the system, and we can determine the diffusion coefficient for tritium in the direction parallel and perpendicular to the bedding plane. So, just to summarize a little bit, which are the most important parameters, we have obviously the radionuclide decay, which is a very well-known equation. We have diffusion, in which we have to understand the role of the geometry of the pore, and then we have absorption, in which we have to include the KD. But all these parameters at the end, especially KD, are empirical. So we need mechanistic understanding to justify the use of the parameter that we provide in PA, and also to develop predictive model in the case of the condition can change. So for this, it's very important to take into account the geochemistry of the system, but also the properties of the radionuclide, the physical chemistry of the radionuclide, both, and especially the radionuclide speciation. This is just a sketch of the possibility that we have, for example, within the bentonite, and to underline the actual importance of chemistry and chemistry evolution. Near to the metal canister, we can have temperature and irradiation gradients, we can have corrosion, we can have the formation of gas, corrosion products. So here we can have also redox effect. We can have chemical gradients due to the various perturbations within the system, but also to the hookup of new water that can change the salinity and the pH of the pore water. Then we can have other problems like the system of saturation degree, microorganisms, and so on and so forth. And also we have to take into account that we will have an evolution with time and that we can have coupled effect to be considered. So we can make experiment to identify each one of these contributions, but at the end we need predictive modeling to assess the effects on the combined effect on the overall safety behavior at the long term. So this want to be an example of what is the application of mechanistic model. I will try only to fix the attention on the KD, but obviously this is valid also for all the other parameters, above all the parameters that are somewhat affected by the KD. So it's important to have in mind that mechanistic and thermodynamic social model is a useful tool to explain the experimental data and to evaluate single processes and to estimate their possible evolution. If we consider the absorption, it is a surface process, so the surface charge is important. It's quite evident that cations will go better in an attraction region than a repulsion one. So we have to understand the behavior of the surface charge. Because also from the surface charge we start to define surface complexes that will help to interpret our experimental data. So we want to relate the KD with the theory or the physical chemistry of the solid surface. So as a first modeling step, we have to have an exhaustive characterization of the property of the clay and pore water, of course, and then we can start to analyze the surface charge and properties of our soil. This is an example of in which we have clays. The zeta potential of clays is always negative, whereas in the case of an oxide, we have positive charge here. Then after the point of zero charge, we will have negative charge. So the difference is expected to, the behavior is expected to be different. The charge can be defined with different models. I will not enter in detail here. Just there are different options to express both surface and potential charge with different models. For example, the constant capacity, the double layer, triple layer, but also we can use non-electrostatic models. So in the case of clays, we know that we can have possibly two important main retention mechanisms. The first one is cation exchange, that is related to the negative permanent charge of the clays. So radionuclide can exchange here at the surface or the interlayer with the charge compensating cations. So the higher the cation exchange capacity is, the higher will be the capacity of the clay to retain radionuclides. But also in the broken edge of the clay particle, we have silanol, aluminol-like sites, which have variable charge, like the oxides. They have less, their density is less than the CAC, but again, they can play a very important role. So, in order to understand how these sites are charged, we have to determine the protonation reaction. So the protonation constant, we can determine the surface charge and then relate them with the theory that I mentioned before. In order to define the surface reaction, we also need to know the speciation of our radionuclide. This is an example of cesium, which is very simple. So there are only one monovalent species in water almost always. But if we consider the europium, which is normally considered as homologous of trivalent actinide, so in this case, we can see in the presence of carbonate that the speciation is not as simple. And we have to consider all these species, trying to see which is most probably related to surface complexes. So we can define our chemical reaction. We have the well-known cation exchange reaction, in which we can determine selectivity coefficient, and then we can make also hypotheses about the possible surface complex which are the absorbed. For example, here is the example of a cation, for a cation a monodentate surface complex. This is a bidentate, and this is the surface complexation for an anion. So in this case, having here the surface complex defined and the one that comes in the solid, we can go from the empirical parameter to equation. So this is the description of the model. So cation exchange is very important processes for alkaline metals and alkaline earth metals. In this case are the example of cesium absorption in a sodium smectite. So cation exchange is characterized by being not dependent on the pH, but very depending on the ionic strength, the salinity of the system. So here I want to observe that one cannot define the behavior of cesium in clay with only 1 kD. So we need to be able to model all the variation. This is the example of the variation of the kD with the cesium concentration and different ionic strength. So in that case, we can see that the cesium absorption is not linear, so it means that there are more than one absorption site with different selectivity that will determine this behavior. The case of surface complexation. Surface complexation is depending on pH and may depend on salinity or not, depending on if outer sphere or inner sphere complex are formed, and it may coexist with the cation exchange. This is the sample of europium, also in the same solid smectite, in which we have here a clear region in which cation exchange is predominating, and then up to from pH 5 to higher pH, we have starting with the dependence with pH, it depends on surface complexation. So we have selected these species to model this data depending on the calculated speciation I showed before. So the problem that we have to face somewhere is to understand which are the processes that can affect safety, because they must be studied with special interest. So which are the factors that can limit radionuclide retention in clay? For example, the ion competence for sorption sites, especially if cation exchange is the main mechanism of sorption. The anions in general are repelled by clay, so absorption can be possible only in the amphoteric site and below the point of zero charge. Organic and inorganic ligands also can limit radionuclide retention in clay, and then the presence of colloidal particles. So this is an example of competitive ions. I will start with europium here. The sorption of europium is in general very, very high, but if we consider the region in which cation exchange is predominant, we have the dotted line will be the theoretical value of the logarithm of Kd with respect to the logarithm of the salt present. So this was the theoretical, so the predicted sorption will be much higher than the real one, which is here in this curve, which bend. This could be modeled, considering that even in homoionic system, there is a small leaching of ions like aluminium or bivalent ions that makes the sorption lower. And this is the case of cesium, for example, so cesium sorption in presence of calcium, of potassium or ammonium, in which each of these ions has a different effects on cesium absorption. So we have to include always in the modeling all the possible equations that we know in order to have a better and more complete definition of the chemical system. This is an example of anions. So anions are negatively charged. It is a problem because most of the long-lived fission products which are of concern are anionic. This is an example of the absorption of selenite in a clay mixture of light and smectite, and in the region of pH of interest of DGRs, the sorption will be very, very small. So we can rely in part to an ion exclusion for migration in clay, and better maybe in redox processes. Because if we consider, for example, the EH-pH diagram for selenium, we can see that it can exist in different oxidation states, from the selenium-6, which is the most soluble, to selenium-2, which has a very low solubility. So low radionuclide solubility generally increases safety, because the precipitation and the formation of solid is a safety function, and so a reduction conditions are very important for DGR. And the solubility product is another important parameter in PA calculation. So we have to mention here also the importance of having updated and complete thermodynamic database to perform all these calculations. Ligands. The presence of ligands entails a potential risk because they may affect radionuclide behavior, because they increase radionuclide solubility, and also they can decrease radionuclide retention in solids. Also, in general, are all negatively charged and tends to form negatively charged species. So the most important inorganic ligands are the carbonate, but then we can have some natural organic in the clay, or we can have in radioactive waste disposal some anthropogenic organics. So this is, for example, an effect of humic acid and citrate on cesium again and europium again. So in the case of cesium, there is no effect at all of the presence of the organic. In the case of uranium, we can europium, we can observe a strong decrease as the concentration of the organic increase. So there are very different effects. So I want to underline again the need of mechanistic understanding and the need of thermodynamic model, because there are still uncertainty on this issue. And then the problem of colloid-driven radionuclide migration. This is not new. This was discovered at least for radionuclide when they observed at the Nevada test site that plutonium could migrate significant distances from the test area. And this was attributed to the presence of colloids, which are particles with small size, high surface area and high reactivity, and that can be very mobile in underground waters. Colloid-bearing radionuclides may be formed by the precipitation of soluble radionuclides, for example the actinides, as occurred in this case, but also by the radionuclide sorption processes on colloids. If we consider consolidated or compacted clay, within them colloid-driven transport is not expected because we have charge effect and also steric effects due to the porosity of the clays. But, as mentioned Reinhard before, we have also the case in crystalline rock, which are fractures, so the water can enter to the surface of the bentonite. The bentonite will form an hydrated gel, and from the gel we can generate particles. So this is important twice, because we can, if a significant clay loss occurs, we can endanger the functionality of the barrier at the long term. And then, because when are formed these particles, that can maybe enhance radionuclide transport. So we made a lot of experiments in order to establish which are the conditions that can favor clay formation and detachment from the clay surface. And this is an example of this experiment that we made some time ago with very different bentonites. So we tried to observe which were the colloidal properties of each of these bentonites. And for example, here there is the dependence of different materials, the generation of colloids, the mass of particles detached as a function of the sodium content. So it's clear that sodium clays produce much more colloids than calcium ones, but also there is some effect on the mineralogy. For example, those bentonites which have higher cementite contents produce more colloids than the others. At least in the case of sodium and mixed sodium-calcium clay. Calcium clay, pure calcium clay does not have an effect on the cementite contents. And then finally, we have also made some experiments to see whether the effects of the presence of this colloid in a fractured media can or not be important for the migration of radionuclides. This is the case of some experiment that we made in granite of the GTS in Grimson, and here we introduce the water plus the colloid plus the radionuclide. So the initial, in that case, the initial absorption of our europium was very high, and at the end we collect the sample in we collect the water in different samples, and we have these breath flow through curves. So it is interesting to observe that when we introduced only the radionuclide, never we observed the breathroom of the europium, in the annealing flow rate. But when we were in presence of clay colloids, then we observed the europium breakthrough and with a retardancy factor of 1, so at the same velocity of the water. So colloid-driven transport can be shown under certain conditions, but still there are various uncertainties about the general behavior and the actual effect on the safety of the system. So these are the main conclusion. So this is more a starting point than a conclusion, but we have shown the fundamental role of the clay in radioactive waste management. In fact, they fulfill all the safety functions needs for radionuclide migration, but in any case, we have still to make special attention to all the factors that may enhance radionuclide migration and all the processes that are not yet completely understood. That mechanistic understanding is needed to support all the decision on the parameter that we have to select for PA calculation, and that interdisciplinary studies are needed for the safety case of a deep geological repository, and that many exciting fields of research are open. So thank you very much